resource person is Dr. Santosh MS from Wipro, Bangalore. I invite our principal, Dr. Ramesh, on stage to introduce him.
Yes. Good morning. I would like to extend a warm welcome to Mr. Santosh MS, Manager, Wipro 3D. Mr. Santosh is a certified trainer for hydraulics, continuous control hydraulics, pneumatics, digital hydraulics, mobile hydraulics, and Industry 4.0. He is working with Wipro 3D since 2023. Previously, he was with Kirloskar Electric Company in Mysore as a trainee from 1999 to 2000. In the year 2001, he has joined as a application support engineer in Temek Automation, Mysore. Then in the year 2002 to 2005, he was working with Sci-Tech Engineering Private Limited as a quality engineer. Then after that, he was working with Chartered Semiconductors as a semiconductor technician from 2005 to 2007. From 2007 to 2019, he was with Bosch Rexroth India Limited as a senior manager. Then after that, he was the senior manager in High-Tech India Private Limited from 2019 to 2023. Since 2023, he is working with Wipro 3D as a senior manager academics. I would like to invite Mr. Santosh for today's session on automation and robotics and 3D printing. Thank you.
Fourth day of the activity? Third day? Fifth day. Okay. So I saw the agenda of the activity. So there were few sessions on Industry 4.0, Industry 5.0. So I just, before I start my session, I just want to understand from you on what is that you have understood on Industry 4.0 and Industry 5.0 also. So that I can align my talk based on whatever has been heard by you. So anyone want to tell what is Industry 4.0 or what is Industry 5.0? Let's be interactive so that it will not be boring for you as well as me. So whatever you feel. So, or else I will frame the question in another way. What is the difference between automation, robotics, Industry 4.0? Is it all related to the same thing or everything is different? Do you feel it is same? Correct. It's a bit different, but it is again just a progress of as the technology goes, we have scaled it gradually. So when you hear the word called as automation and robotics, so whenever I talk about automation, I generally refer it as industrial automation. Because automation can be anything. It can be home automation also, or it can be your robotic process automation also. It can be automation in the banking sector also. But in this particular session, whenever I'm saying automation, I'm only referring to industrial automation, or we can also call it as factory automation. So, whether is there a major difference between automation and robotics? Or it is again the same? Whenever it has some movements, robotics. Correct. And otherwise, we can generally call it as an automation. So I'll skip few of the slides here. So this was prepared by me during my previous organization. So I'll skip few slides and get into the topic straight away. So what is automation? Why is it needed? So now there are a lot of new technologies which are coming, like say Industry 4.0, it is there since one decade. And now we are talking about already Industry 5.0. And to be very frank, it is a very big subject. Industry 4.0. Now, though it is a huge subject of interest, we also need to see on the practicality issues. So, India being a country which is a developing country, a very quickly developing country, and at the same time, since the last 1 decade, Indian government and we are primarily focusing on manufacturing as the main thing. So before 10 years back, we were all being focused on service theme. That is where the boom of IT and everything came, and it has got its own place. But over a period of time, we realized that for a developing country like India, it's not that we become a service-oriented company, but we should also self-sustain ourselves by introducing or making the market manufacturing. So when that was realized, we started concentrating on manufacturing, and then it became popular as Make in India projects. So Make in India product is given more emphasis uh, by the government also and private also is being adapted in a very large scale. So whenever we say manufactured in India, so any process has to be automated if you have to have productivity. So just again to keep you all involved, now everybody knows what is automation. It's a general topic, so I don't want to get into very basic concept. So now when I say automation, what is the advantages of automation? It's a very generic question. Why automation is needed? What is the advantage of it? Errors can be avoided, correct? Productivity can be increased, very true. Reduce the downtime, yes. Quality can be improved, correct. Safety aspects can be given more importance, very true. Accuracy can be increased, yes. Something similar to accuracy, repeatability can be increased. Anything else? Okay, most of the things have been told. With so many advantages, what is the disadvantage? High cost. But again, when I look at a general thing, initial cost will be higher. But after that, how much ever you try to optimize it, your running cost can be reduced also. Any other disadvantage? Creativity, yes. Limited? Correct. Scalability. Whenever you have a change in the process, if you have to enhance more number of inputs or more number of sensors or more number of actuators, that will be limited by the hardware which you have used for the automation. So scalability, yes. Anything else? Safety we can enhance. It all depends on how we do the automation. So my point was, so every technology has got its own advantages and disadvantages. But at the same time, we also need to know why automation is required. And for each and every mission, automation might not be required. So we need to first identify whether it is really viable to do the automation. If I am doing the automation, what are the other criteria which I need to take care? It's not that everything we automate. Now, just to give you an example, I am wearing a smartwatch. So, how many of you wear smartwatch here? So many people. So, how many of you regularly exercise, walk, keep a track on how many steps I have much calories are burned. Let's see, at least I saw 10 people raising their hand, but this question only one person is raising their hand. So again, in the same thing now, whenever you buy a smartwatch also, you see that, okay, this has got SpO2, oxygen level monitoring, heart rate monitoring. So it is a good thing to have. Now, say tomorrow, in what ways it should not happen, you are getting a heart attack. You monitor and it is going to above 200 beats per minute. What is it you are going to do? Nothing, right? So, automation is something similar to this, so you can, if I have to simply automate a simple conveyor, I can simply put one motor and automate it also. I can put a servo motor, a lot of sensors, and I can make that machine or a conveyor automation starting from 1,000 rupees all the way to the 1 crore also. We can spend on automation. So first, very basic thing is why automation is needed and whether it is really needed. Okay. So I've got a small video because just as a morning cheer up, I just wanted to share a video. I'll just show you. I'm sure most of you might have seen this movie. It's a very old movie. See, it's a production line. Since you all know Industry 4.0, this was somewhere Industry 2.0, between 1 and 2. So, in this particular video which you all seen now, did you find any automation there? So, which were the automation which you could find there? Conveyor, correct. Then the speed of the conveyor in which they were controlling the levers and all. So it was basically a steam. So through that they were adjusting the pressure, they were controlling the speed. Now, if I ask you people, what automation from the more can be done here? What can be done? Tightening of nut and bolt, correct? Punching system, yes. Correct. And no safety also. So you can implement safety. Correct? And quality, by mistake, one of the nut and bolt or one of the stamping is getting missed. So that can be implemented. Now, again, going a bit deeper into the same subject. Now, you told you that you if given an opportunity, you will automate the tightening process, correct? So, which technology will you use to do that automation? I'm sure there is a mixture here, and I understand that we have got mechanical as well as electrical faculties and students here. So, given an option, you told it's the right point you told that tightening that particular nuts can be automated. What will we use to do that thing actually? Pneumatics, okay. Any other option? What is the working medium of pneumatics? Air. Right. Robots also can be used. So typically, a robot thinks it is controlled by electric motors. Or to be very precise, servo motors, which have got high accuracy. Correct. So robots can be used. Only two options. So how many of you are from mechanical here? Okay, very few. So in mechanical there is a subject called as fluid mechanics. So under fluid mechanics we discussed only on one thing, that was pneumatics. So the other is hydraulics. So even hydraulics also can be used here, right? So we can use hydraulics, we can use pneumatics, we can use electrical motors also to automate this process. Now, which one is best suitable? Hydraulics, pneumatics, or electric motor? Which one is best suitable and why? Okay, let us not come to this. Let us make this application a bit more generic. Say, for example, all have traveled by buses nowadays. So nowadays buses comes with automatic door opening and closing. So the driver will hit a button, door will open and close. So what is used in the buses? Pneumatics. Is that the only option? Hydraulics can be used. Majority is electrical, nobody is batting for motors. See, simple thing. Now, this mechanical will understand it a bit more. So, air means I cannot simply take the atmospheric air and use it for the movement. I need to compress it. So, I need a compressor, then use a pneumatic. Similarly, if it is hydraulics, its medium is oil. I need to circulate the oil and then control the movement. Now in any buses, battery is a mandatory thing, correct? So the simplest way is putting an electric motor now. I don't need a compressor, don't need a hydraulic power unit. I take the power supply directly from the battery, put one DC motor, and to increase the torque I put a gear. So gear DC motor I put. I open and close the bus door. Why still people are using pneumatics? Let us imagine air compressor is not there. That bus doesn't have what the air suspension not there. More force even in today's thing, whatever hydraulic can develop the force, 80% of the force electric motors also can produce. And the size will become bigger than some. But it is possible. Why don't we use electrical motors? Complication is much easier, no? Take two wires from battery, one will connect a switch in series, other ones connect a motor. Okay. Now I give you, I ask questions, right? We can use hydraulics also, we can use pneumatics also, we can use motor also. If I implement any three, the bus door will still open and close. Now main thing is, let us see hydraulics. Hydraulics, the working medium is oil, fluid. So tomorrow, if there is a leakage in that particular actuator, people are boarding on the steps only, no? So if the oil falls on that particular thing, people can slip and fall down. So it's a safety concern. And that is the reason hydraulics will not be used. Same way electrical. Once wire gets peeled off, it comes in contact with your body of your bus, which is completely conductive. Everybody sitting in the bus will get a little bit. Okay? So again, a safety issue. Whereas pneumatics, it is compressed air. What happens if it leaks? It will get mixed up with the atmospheric air and so on. So considering that safety point, see now, just try to understand my point is, to do an automation, you have got an option of electrical, hydraulic, pneumatic. But still we have selected only pneumatics there because considering the safety. One more example, say Kerala is completely a terrain, mountains, that is not even a plain landscape. So I could see a lot of JCB, Bobcat, Caterpillar machines, earth moving machines, heavy machines. What technology is used there? Why not pneumatics? Why not electric? Pneumatics, it is very clear. Since most of you are electrical, the main air, which is the main working medium in pneumatics, is a very highly compressible medium. So you cannot generate more force and pressure. Whereas hydraulics is a highly incompressible medium. So by which you can generate high pressures, high force, which is required for digging and lifting also. Electrical you can match. You can put an electrical motor and still make it work to match that particular force which hydraulics is doing. Why electrical is not used? Power consumption. You cannot decentralize. No, then I have to literally search where the electric poles are there, put wire and draw electricity from there. Not feasible. Or if I want to store that particular amount of electrical energy, the size of your battery or generator will become again very huge. So there, the best suited one is hydraulics. So hydraulics is used. Now similarly, you have got electric fans here. Why can't I use a pneumatic motor or a hydraulic motor here? Why electrical? Correct. So here again, if I have to generate that particular pneumatic energy, I need a compressor. And if I need hydraulic energy, I need a power unit. And here the force is not much. A simple electrical system would work here. So whenever you come across any sort of machine, you have got plenty of options. So that was my next point. What technology goes into a machine or automated machine? So few examples which I have given you was hydraulics, pneumatics, and electrical. Similarly, it can be a pure mechanical system also. You can adapt anything, you can automate anything, but at the end of the day, you need to check all the other aspects. The force required, the pressure required, the application, the safety. Considering all these things, then we have to decide which technology has to be used for automation. Is it clear? So we had just made a comparison of different technologies. Typically, wherever very high forces are required, where the best suited one is hydraulics. But again, alternatively, you can match that with electricals. But the size ratio, hydraulics to generate the same force, the component might be only this many size. But if I have to generate the same force using electrical, the component will be much bigger. When it comes to safety aspects, nothing safer than pneumatics. So there are multiple options for you guys to select which technology we have to use. So looking at various aspects, you need to pinpoint on one technology which can be used. Okay. Now, I also told you that India is a developing country. Now, there are several industries in India which has been classified also. Large scale companies are there. Similarly, medium scale enterprises, small scale enterprises, and such kind of things. Now, you go to any industries, you'll see one or the other automation being implemented either on the machine level or on the entire factory level. It depends on the size of the industry. Correct? So now, if I generally see which are the predominant industries which are working, basically I can classify it as steel sector, cement, automotive, railways, mining, machine tools, press, defense, oil and gas, power, and even mining as well repeated 2 times, and power. So you take any industry for that matter. You take a steel sector, you take cement, automotive, any sector, you will find hydraulics, pneumatics, sensors, PLC, electric drives and controls, and robotics also. So in this particular graph, you can see hydraulics is predominantly used in steel and cement. Automotive is a bit lesser because we don't need that much amount of power. Mining, predominantly it is hydraulics. Machine tools, when I say machine tools, it is CNC machines. Basically, your lathe or milling machine or vertical milling machine, such kind of things. It requires only for certain operations only hydraulics. The rest is all electrical. So, every industry has got its own share of hydraulics, pneumatics, PLC, and sensors. So, these technologies form the basics for your automation. So, when you end up, many of the students here, when you end up into a job, you may not happen that you will use all the technologies, but you may end up using any one of the technology. Some people may get into something called as PLC programmer, where you'll be constantly writing logics for the machine. Few of you may get into design aspects of hydraulics and pneumatics. So there a lot of calculation of force, pressure, such kind of things, and selecting the components also. But irrespective of any industry, you have got potential for all the technologies. Now, but this is a statistics predominantly done for India only. So if you see, we are a nation where we are a very aspiring nation. So we want to implement the technology, we want to know the technology, but if I generally visit a lot of industries, many of our industries are still stuck in industry 3.0. And when it comes to small scale and medium scale, we are still with 2.0 also. But now we are already as a technology and learning aspect wise, we have reached 5.0. So generally, if you see the robotics itself, robotics is very minimally used in industries. Two prime reasons. One is not a technical reason, but with such a huge population and such a huge and the manufacturer provided programmer, and gradually it became in such a way that a software which you can install it. Even today, 90% of the PLC application, every company provides their own software to program the PLC. So what is the next generation going to be? I am sure my old friend, the first session of the FDP, Mr. Milind Tavre, he addressed on Industry 4.0 and 5.0. So what is today's generation PLC works like? So today we are in a generation where we call it as open code technology. So which means if you have to program a PLC, you don't have to learn PLC programming language alone. You know C programming, you know Python programming, or you know JavaScript or Visual Basic Script. You know any one, use your own language and program the PLC. So nowadays PLC can accept a wide range of inputs or command or instructions. So the trend is changing. So this has not happened in the last 5 years or 10 years. PLC first got introduced somewhere in 1980s. And now we are almost 45 years now from the inception of PLC till date. And this 45 years, the technology has grown from a simple microprocessor till a stage where not only on-off signals but analog signals, fuzzy logic, AI generated tools, data analytics, everything can be implemented into a PLC. Same thing with hydraulics. Right from a simple basic hand lever operated hydraulics, today we are in a generation where the hydraulic components can evolve or teach on its own. You operate few cycles, it will learn the pattern and then it will start adapting to it. So we have come to a stage till there. So mechatronics is a general term which we use. So it is basically a combination of all the technologies, whether it's electrical, mechanical, computer science, electrical and everything. Now, since my introduction was given to all of you, correct? Now I have ended up working in the industry for almost 24 years now. Since 24 years I have been working in industry, but Ramesh sir read a big list of companies. So I had got a very, you can say it as a good habit or a bad habit, changing the jobs. So in the initial days of my career, whoever used to offer me good salary, I used to jump. So I started changing companies. I started with CNC company, went into automation, then went into security control access products, then went into wafer fabrication, not the ice cream cone wafer, semiconductor wafer fabrication, then went into hydraulics pneumatics, continued with hydraulics. Now I have switched over to 3D printing. Can you tell what is my background? Whether I'm a computer science, mechanical, electrical. So, what I meant to say is, though the technologies are different and your areas are different, but when you end up in an industry, it really doesn't matter which stream you belong unless and until you can fulfill the given task. So my background is basically electrical electronics. But to be very frank, I am very comfortable with hydraulics and pneumatics. Problem was I couldn't see electrons. Hydraulics, at least I can see the oil coming out, air pressure I can feel. Concepts are all same. It is only how you apply your mind and understand that particular process. So mechatronics is one thing which is everything. So I am a jack of all, master of none. If you ask me to go into deep into any subject, I don't know. If you ask me anything a little bit, I know. That I am trying to share with you all. So there can be a lot of different kind of mechatronic system also, and robotics also you can name it as one of a mechatronic system. It's not that it is very unique technology or anything. It is nothing but a combination of your electrical, mechanical and IT. Output product is called as robotics. So these are all we have covered during the starting. So here also I don't want to bore you with the history and all. Basically robotics was not at all meant for a technical term. It was basically a Czech Republic drama which happened in 1921 where they first introduced the term called as robotics, which referred to slaves. And over a period of time when we started doing advancements in mechatronic system and all, we adapted this word called as robotics. So I think these are all known to you. I don't want to bore you with such kind of things. You can Google and get it, and even I can share this presentation and you can have it later. So main typical robots which are used can be classified into two aspects. One is industrial robot, or you can refer it as stationary robots. Whereas the other one we can call it as mobile robots, which is not in a given stationed position. It will be continuously on the road. So you can read a lot of applications also here. So when it has to do a continuous repetitive jobs, then it can be something called as metal handling, picking from here, placing it from here, or inserting a screw. That's a routine job. Then welding, inspection. Inspection in the sense I can even include a camera on the robot which will take the picture, compare it with some standard good pictures and say that whether your quality of the product is good or bad. And mobile robots, it all started, I think even the students will be into some competitions, rover competitions or racing car competitions. And nowadays even you design a lot of rovers for sending it to the space also. By any chance, have you been participating in the ISRO basket? So students who are interested, no, every 2 years or 3 years, ISRO uh, gives a lot of problem statement. They called it as a ISRO respond basket. So similarly, HAL also does it and government agencies does it. So basically it is open only for institutions. So what you can do is you can go to this particular ISRO basket, read different problem statements, and if you think you can provide a solution, you can write a proposal, send it, and they will fund it to you. It can go for 3 years, 4 years. They'll spend crores together and they fund it, and you can pursue that also. So this one area which most of the sectors are being implemented now. So I'll skip all this part. So ideal task, robot also not everywhere needs to be applied. So only typically when it's a repetitive job, you're killing a human's creativity. And second is, say for example, I have to pick and place it and tighten it here. If I've quarreled with my wife from home and come, that anger will show in the work also. I will not tighten it properly also. Machines are safer in that way. So they do good repetitive things. And second is wherever humans cannot reach in a very small area or very hazardous area where poisonous chemicals are there and such kind of things, we can use robots. And this is one trending topic now, which is surgeries. You might have heard about robotic surgery, robotic precision way. So again, there also predominantly technology is being used. So as I said, robotics is not of one discipline. So many disciplines get into robotics. It's mechanical, electrical, electronic instrumentation, system engineering, and even computer science. And today's generation, even AI, ML, data analytics, everybody have got a role to play in the advancements of robotics. So generally, how do you specify a robot is very important. So there are many different models of robots. So when you want a robot, how do you ask for it? So generally, the first thing is payload. Anybody knows what is a payload? How much weight it can lift. Say for example, if this hand is a robot, so this will become 1 axis, 2 axis, 3 axis, and then if I have to lift this, what is the weight I should be able to lift is called as the payload. Second is reach. How far your robot has to reach. Then what is the accuracy? So here the cost really changes. So you can simply do it with the induction motor also with very um, coarse accuracy, or if you want very high accuracy as low as 1 micron, also you can get the accuracy, but there you need to end up using servo motors. Then repeatability. If I do the same task every time, what will be the repeatability or what will be the deviation in the end position? So these points are very, very important when you have to specify a robot. Same thing I have explained. So this presentation will be available to you. You can read through it. So some of the disadvantages of robot is lack of decision making power. So whatever we program, it just follows it. It cannot decide on its own. loss of power, so you are moving somewhere and somewhere it has stopped. So you cannot resume it from here, but you need to come back to your home position and then start resuming the things. Damage to robot and other devices. So if I have programmed this robot to keep it from here to here, and by chance something comes in between, sometimes it will not be able to oversee that and it will go and hit it also. It can damage other components in the machine, or even it can cause human injuries also. Now, this was a slide which I prepared 7-8 years back. Is this all true till today? Have you heard about something called as collaborative robots? So what is the difference between a normal robot and a collaborative robot? Pardon, sir? Correct. So collaborative robot, it can work in coexistence with other robots or even human beings. And that will not lead to these accidents. That is called as collaborative robot. Interesting. Now what is the difference, but? Correct. So, correct. Now if you generally see, collaborative robot also does the same things which a robot does. But safety aspects wise, it is far more superior. So like nowadays, iPhone you get a lot of different variants. So iPhone 14 to 15, one small change, but it will be a totally new model and a totally new craze in the market. So in collaborative robot, what has been done is basically on the surface of the robot, there is a capacitive skin put on it. So this predominantly electrical will know more capacitive sensors. You heard about capacitive sensors? Inductive sensors? Difference between inductive and capacitive sensor? So basically a lot of different kinds of sensors are there. Say inductive sensor, we can only detect metal. If I put my hand in front of the sensor will not even sense me. Capacitive sensor will sense everything. It will sense everything. So what we do in the collaborative robot is, on the layer of the robot, a capacitive skin will be put. So any human or any object which comes close, the robot can sense it through that particular skin, and by which it will reduce the speed of operation or it will stop. It will take a pause. So when I take out my hand, it will automatically start resuming the function. So with this, it can collaboratively work in an environment where everything is put close together which can touch each other also. So that's the advantage of collaborative robot. So literally, it's the same robot packaged with some advanced sensor technology. So disadvantages of robot, some more here. Initial costs are very high compared to a conventional automation system. Whenever you need to expand, you need a lot of other peripherals. So like tomorrow you want to incorporate a vision sensor. So a vision sensor has to be had separately and then integrated. So different elements of robot. So robot is only not one thing. You've got an end effector, you've got an axis, you've got a manipulator, and many such kind of things. Mainly manipulator is your structure and which creates the joints for achieving the degree of freedom. End effectors is basically uh, the gripping mechanism or the tooling mechanism or insertion mechanism, whatever you want, you can have. The robot can be a simple thing. In the end of the robot, you can put a welding torch. You can put a two-jaw gripper to lift any component. Or you want to pick a round objects, a three gripper. So end effectors can be, possibilities are endless. Actuators, so depending on your accuracy, you can have either hydraulic cylinders, pneumatic cylinders, stepper motors, and very high accuracies, servo motors. Sensors play a very critical role in any automation. So we generally call it as, for any automation system to see what is happening, that is only possible through sensors. So without sensors, any automation can be considered as an open loop system. There is no feedback, it is simply doing certain things. And some things are closed loop, where you continuously see what is the error and correct it and do it. So to do that, you need a sensor. Controllers are all brains of the robots. This is where exactly your strength of your robotics lies. Now say I can simply put 3 axes. Now say for example I am in this position, my robot is here. I need to pick this material. So one thing what I can do is go like this, come down, pick it up. This is a simple system, still it's called as a robot. But your controller can be enhanced in such a way that now time taken here was going here, going here, going here. Now simply I can go here. Correct? Now when I am going here, I cannot go straight away like this, I hit the mic. So I can program in such a way that I can go in a circular kind of pathway or a straight pathway, or I can say move via this particular point. So it will go here and then go here. So there are a lot of coordination function. So multiple axes working together in a sync. It's not that only one axis has to move at a time. Every axis, if there is 4 axes, 5 axes, 6 axes, everything can work in coordination with each other. That is the beauty of robotics. That is called as even kinematics, where you develop such kind of logics where you can define the path to go straight away point to point or via a point or in a circular interpolation and such kind of things. So that's the strength of the processor. And last one is the software. So how do you want to give an input to your robot? How do you program your robot? All this logics of interpolation movement is already built inside the controller. But you need to give instructions for it to activate. So that can be a user end software. So I am a user, how do I interact with my controller and program it? So that is all about the software. So this I'll quickly glance through. So very basic is a Cartesian robot, a 3-axis or 2-axis. This will be the working space, a cube. For this robot, whatever it operates, it can operate within that particular window. Then we have got something called a cylindrical robot, where the working area will be within that particular circular shape. Then you have got spherical. So the working area changes. Then comes the most advanced and most widely used robots, articulated robots. So which will have a much larger reach, flexibility, agility, precision and easy to use. SCARA robots. SCARA robots is just like your hand. We call it as left hand operation or right hand operation. So in your left hand operation, now say for I'm here, I can reach here, reach here, reach here, reach up to certain length. Behind this I cannot reach. So whereas if I have to reach this position, then I have to go for a right hand SCARA. So it is just like your hand. So at the same time, coordinate systems. Robots follow different coordinate systems. Now if I say for example the robot has to move from my existing position 2 steps to the left, I'll go 2 steps to the left. Now I'll say 3 steps to the left. Now whether I'm referring to from this position or from my home position. So that defines a different kind of coordinate systems. So in this way we have got a joint coordinate system, a basic coordinate system, world coordinate system or workpiece coordinate system. Maybe you don't have to know everything. We say world coordinate system means yes. So world coordinate system means from my home position everything will count. So 2 step means 2. 3 means from this 3 steps. So if I am already into second step, I have to just take 1 step. We can also call this as absolute or incremental positioning also. Workpiece coordinate system means this is my final object on which I am going to work. So this point I will consider it as 0, 0, 0 and from here I will define all the movements. So it is basically a robot will work with anything. So user wise, if you have to be flexible, it's easier. So this part I am going to literally skip it. The reason is I saw the agenda, there were at least 2 sessions on Industry 4.0 and 3.0. So I will not go into that. So this is not my contact details, this is my previous organization. But my phone number would remain the same. Email ID has changed. So which I will share it in the last. So till they join, I'll just play one video. Basically 4.0, 5.0. Now this video is not anything related to industry, but the more and more emphasizement which is given in industry 4.0 and 5.0 is data. So once that data about that particular domain is there, it can be converted to any sort of knowledge and implemented. Just to showcase you, I am just playing a very small video. So this is a product which is there is some issue with the audio, which probably at the end of the session we'll see this video, or else you can just search for Google tulip. So tulip is basically a flower plant. So they have collected a data, and over a period of time they have developed algorithms and some models of communication where they can speak to the plant, what it needs, when it needs, even general conversations also you can have with the plant. So we can end up to that. So now coming back to our session, the last topic which I want to address is additive manufacturing. So anybody knows what is additive manufacturing? Correct. It is creating a 3D component by depositing material layer by layer. Now, this is not a new technology. It is almost 20-year-old technology, which was already there. But over the last uh, 5 to 10 years, the importance of this particular technology has tremendously grown. Now, since my salary comes from Wipro, so I'll just give you a brief introduction about Wipro before getting into the topic. So, everybody have heard about Wipro? What is it you heard about Wipro? IT sector, lot of products and service business. So, in fact, 1 year back when I joined Wipro, even I didn't knew what Wipro was. So, Wipro, the name itself, it was based out of their first business. You know what is the first business of Wipro? Palm oil. So, it is Western India Palm Refined Oil, which is Wipro now. So, it's one of the biggest MNCs. They've got a lot of products which you are using but you are still not aware of it. One is most relatable product is bulbs and CFL and LED lamps, which Wipro manufactures. Wipro lighting we call. And apart from that, Santur soap, Yardley, Chandrika, all these products are from Wipro. And apart from this, we are also into Wipro Hydraulics. Similarly, Wipro Aerospace, Wipro Automation. So previously there was a company by named Pari Robotics, which was very famous for robotics. So that company was acquired by Wipro. Now it is Wipro Pari we call, Wipro Automation also we can call. So Wipro is also into healthcare in collaboration with GE. And Wipro and Kawasaki are collaborated for high precision components also. So this all belongs to something called as Wipro Enterprises. Wipro Limited is only IT. So the bigger part which was not known to you, I've just given you a brief background. So somewhere around 13 years back, Wipro decided that we need one sort of business which will focus on the emerging technology and which was identified as additive manufacturing. So we started as only a service provider for additive manufacturing. So now the concept of additive manufacturing, as you imagine, it is depositing a metal or a polymer melted one over the other to make a component, something like this, say for example. Now everybody's perception when it comes to academic side, it's polymer, plastic. But we started with metal. We print a lot of different grades of alloys. So some of the names of alloys which I can tell is aluminum, titanium, nickel, copper, cobalt chrome, super duplex stainless steel, then something called as Inconel. So all these materials can be 3D printed. Similarly, polymers are also 3D printable is possible. In polymers also you have got lot of different grades of polymers, right from something called as PLA, ABS, TPU, HIP, peak material. There are different grades of materials. So why I am telling you all this particular thing is, when it comes to the industry wise, most of the industries are adapting additive manufacturing as one of the prime manufacturing process. The reasons I'll tell you a bit later. They are adapting additive manufacturing over conventional process. The same trend we are seeing in academics also. So most of the academic institutions, they are working on methods of 3D printing. Second is different kinds of materials of 3D printing. So whether say tomorrow cast iron, whether it is printable, mild steel, whether it is printable, brass, whether it is printable, gold, which is printable. So lot of research is going on one is material study and creating new alloys. So there are a lot of institutions who are working on aluminium alloys. Say aluminium, silicon, magnesium. Put together it can become a super alloy which will have better strength than aluminium. So similarly many researchers are working on material process and the strength from this particular process also. So 12 years back we started with metal print services. So any industries used to come to us, I want to manufacture this component using 3D printing, we used to print it for them. Similarly, as gradually this business became bigger and bigger, we thought that we should come out with our own machines for 3D printing. So then we came up with our own filament based polymer 3D printing machine and then resin based 3D printing machine. So in today's date, Wipro 3D provides print services, printers, and when it comes to academic institutions, we do 1 credit program, 2 credit program, 3 credit program, and if there is a mechanical engineering, we can support an honors program, which will go on for 4 semesters with 18 credits. And similarly for other streams, we do minus program, which will again carry 18 credits. So we have got a lot of engagements towards academics also. So given said that, I'll get into the topic now. So the first basic, apart from additive manufacturing, how it is being conventionally manufactured. So everybody knows casting here. So you can just click on that, it will play a video. So casting is basically you got a mold and you melt your metal and put it into the mold so that it will take that particular shape. So this is casting. So most of the components which is bulk manufactured are still using casting process. So otherwise next is forging process. Forging is by compressing it, whether it's with heat or cold forge or any such kind of things. So you are heating it and bending it into a shape. Second conventional method is forging. Okay, so this is the conventional forging process. Next is forming. See, bending the pipe to different shapes. Most of your automotives, your silencers and such kind of things, everything uses forming process. So pipe is bent and cut here to a particular shape. Punching holes into a sheet metal. So this is one more method of conventionally manufacturing things. Next is something called as subtractive, which most of you are aware. CNC, you take a solid part and then take out or subtract the unwanted areas from that by using a proper tool. So these are all typically general different ways in which we manufacture certain mechanical components. Now the new method is additive manufacturing. So you understand the terminology. This is subtractive manufacturing, means you are from existing a bigger piece, you are taking out unwanted or other part and keeping only the shape which you need. Whereas in additive there is nothing wastage there, but you are going to melt and only deposit it layer by layer by layer by layer in order to form the complete component. Now, when it goes into mass production, that means I have to manufacture this 10,000 components. Then the best is such kind of process itself, because once process it is set, it is done. Now I want to design this product for the very first time. Okay, first prototype I want to do, first product I want to do. Now can I make a mold first, then pour it, and then I will see that no, this angle should have been a bit more. Then my mold is gone. I have to make a new mold again, produce the component, which itself is a very expensive and a very time consuming process. Suppose if I do all the design and if I'll be able to print one component, so printing this would take roughly around 1.5 hours. So if you can print it and then study everything, and then you can go into mass production by your conventional process. So basically when 3D printing or additive manufacturing when it was introduced, it was basically focused on only one thing, is rapid prototyping. So you have done a design, you want to realize that design, and for the first time you want to see how the actual component looks like, or how it functions, or how it goes into a bigger assembly. The easiest way was 3D printing or additive manufacturing. So, but over a period of time now, certain things have become more flexible with additive manufacturing, and we have come to a phase where certain parts we find additive manufacturing cheaper than conventional manufacturing. So gradually over a period of time, additive is manufacturing is taking over the conventional process. Not everything, but certain aspects. So recently you read in the newspapers probably LPSC, anybody knows? It's a division of ISRO who tests the rocket engines. So earlier the rocket engine was manufactured conventionally, where around 16 different sub-assemblies were brought together, assembled together with nuts and bolts, weldings, where some 19 welding joints were there. And it used to weigh approximately 500 kgs. So for the very first time in India, we partnered with ISRO. We have partnered with ISRO since last 12 years. For this project, we took it up, we jointly did the R&D, and this rocket engine was 3D printed. And recently, 2 months back, it was hot tested in LPSC in Trivandrum. and it was successful also, which came in all the newspapers. So Wipro's name was there, kindly go through. So it is having a lot of breakthrough technology which is getting implemented in most of the areas. I just gave you one space application. It's not only space, even in automotive, even in general automation, even in medical. So suppose you break your bone, you need to put an implant there, say for example. Now implant, if you go to the present market, you got all standard implants. One with 10 mm, the second size is 12 mm, and so on. Now every human body is different. So that may not perfectly fit you, but you don't have an option, but whichever is closest, we adapt to it. But today we have come to a generation where once the CT scan is done, from there we take that particular scan and convert it into a 3D model, and from 3D model we identify which part has to be done, and that medical implants we print it, and then that will be used in the surgery and it will go into the human body. So 3D printing has got its own place right from a simple student project all the way to aerospace and medical applications. So this is how additive works. So it is melting a wire or a powder of metal and depositing it layer on layer. So the process is a bit slow, but when it comes to the first prototype, it is always faster. There were a lot of different techniques shown. I will show you that in detail also. So typically, your additive manufacturing workflow will be initially your CAD creation, a 3D drawing. So which you may end up using SolidWorks, Pro-E, CATIA, Fusion 360, anything. So you do your 3D model, then that will be imported into a 3D modeling software. Then we have to decide, in critical thing in 3D printing is, if say for example I have to print this. So whether I have to print it like this, or print it like this, or print it like this, any direction, I am okay to do anything. But we need to understand that 3D printing is a layer by layer process. Say for example, if I want to print it like this, I'll print this layer, this layer, this layer, somewhere I'll print in here. Now when I have to print this layer, I don't have any support in the bottom. So if I melt and put it in the air here, it will come and fall down. So it is not possible to print like this. So I have to optimally decide in which direction it has to be printed. So in this direction, I can print it here, but again, if I closely see, on the top it is flat and here it is hollow. So if I want to print this flat surface, it will fall down. So what this software can do is, it will generate supports. An additional thing which will be printed from layer 1, and that will help in printing the finer flat layer. So these supports are also designed in such a way, or the software does it in such a way that I can use my hand or a simple nose plier to pull it out, it will break off. This will be built with bigger thickness, stronger parameters, whereas support will be lesser strength, can be removed easily. So we'll have to decide on what is the orientation, and then what it will do, this 3D model, it will get sliced into many different parts. So then this sliced thing will go into the machine. So machine will take only the first slice first and only deposit that. Once that is done, second slice, third slice, fourth slice. Like this, it can be thousands of slices one over the other, it will start doing the function, and finally your finished product will be available. Clear on how 3D printing works? Got a rough idea? So, based on the standards for additive manufacturing, we call it as ASTM. So, under this, we have identified so many different process of 3D printing. So, first one is VAT polymerization, or we can call it as stereolithography also. So, this raw material is resin. Anybody knows what is a resin? It is in a liquid form. It will be a bit thicker, but it will be in a liquid form. So this resin, various different kinds of resins are available. So if you keep it for drying, some things will become hardened. Or some things, when you expose it to UV light only, then it will become hardened. Some at laser length of say certain wavelength only, it will harden. So we use such kind of resin for 3D printing. So what happens is basically, I'll just give you an example. We use a UV light. So this is a screen, same as your mobile screen, but which will emit UV light. So on this, what will I do is I'll put a transparent tank, and inside the tank I'll fill it with resin. Okay. Now once I do that, I'll have something called as a build plate, which will be the same shape as your say mobile only, the tank size. So now what this build plate will do is, I'll put it exactly down like this. Now in this particular display, I will flash the first slice. When I flash that particular thing on the screen, only that portion of the resin will get hardened. Next what I'll do is I'll lift this particular build plate slightly above. So resin will fill again. Second slice I'll project the image. Like this I can keep on taking it up and flashing new images by which we can bring out a 3D product by itself. So this process is called as VAT photopolymerization. Second one is easy. It is metal extrusion. In this, we take wires, polymer wires or metal wires, predominantly polymer in this case. We heat it so that it will melt, and there will be a small nozzle by which that material will be pushed out. So that material we start depositing it layer one over the other to build a component, which we call it as FFF, means fused filament fabrication. The next one is material jetting. So in this basically what we will do is, instead of using wire or resin, we use powder, polymer powder. So this polymer powder will be, each powder size will be around 30 microns to 50 microns. So that powder, what we do is, we spread over a layer with a thickness of say 100 micron or 50 micron, and then we pour some resin on it, on wherever you want it to get hardened. So that resin, once we pass some light, it will get hardened. Next what we'll do is, we'll put one more layer of powder on that, again put resin wherever it needs to be hardened, again expose it to light. And like this we keep on doing it to achieve a component. The next one is very similar to material jetting. In binder jetting we don't use resins, but we use some chemical by which automatically your powder will get hardened. That is called as binder jetting. Next is powder bed fusion, predominantly known as LPBF. So laser powder bed fusion. Okay. So in this also, so this is predominantly polymer, whereas this you can print 3D components from it. Okay. Similarly, MJF is multi-jet fusion, very similar to binder jet, but it can do metal also. This is electron beam powder bed fusion. Only difference between these two is this is laser, this is electron beam. That's all. The next one is direct energy deposition. So this process is very similar to your FFF. So here we'll take a wire of metal wire and melt it and deposit it. Okay, so that melting can happen through laser, electron beam, or it can be arc melted also possible. And last one is sheet lamination, means you put sheet one over the other and press it together. That is also possible. But these are standard processes defined by and accepted globally. But widely used is VAT photopolymerization, FFF, LPBF, binder jetting, and DED. This is, I've been in this industry since 1 year. I have not even seen a single component or whoever does this. So this it is almost neglected. These things are used but very rarely, but predominantly LPBF, FFF and DLP is what is predominantly used. Any doubt in this? So any doubt in this, or it's clear? There are different processes, but everything is done to produce a component itself, ultimately. So here you can see some examples also. These are all done in our own manufacturing plant in Bangalore. So this is Sir M. Vishweshwaraya statue. We print it for some institutions to give it as a memento itself. It's a bit expensive, but here in this particular printer you can do color printing. Means literally not everything in one color, but say the turban you can put one color, coat one color, skin color. It can be as real as it is possible. No. So these are some of the examples of fused filament fabrication, where this entire thing is 3D printed. So using polymer material. And nowadays you see a lot of ad on this Tootsie transparent tooth aligners. So basically they also do the same thing. They scan the teeth dentures. They first print it in VAT photopolymerization, and on that model they put a transparent sheet and vacuum cast it, and that they sell you as transparent tooth aligners. Similarly, these images which you can see here are again 3D printed, color printed. So basically when it comes to additive manufacturing, the key things which are very important is, one is material selection. So what kind of material I need, what should be the properties of that particular material, and even what kind of strength that particular materials will provide. So like this you get lot of manufacturers. So to be very frank, till the last 5 years, we didn't had any manufacturer of powder in India. Now we have got 4 or 5 manufacturers. But when we tested everybody, we have only one powder manufacturer is qualified in that, who can support with the best quality. So we have got good suppliers in India also now. Next is aim design optimization. Now, as I told you, aim design I cannot simply print the same model because there are something called as overhanging features where I need support. Say for example, this component, if it has to be printed in the incline, all this bottom portions, whatever you are seeing, is support structures. So it is not even mandatory that if my design is this, I need to retain the same design. There is a concept called as topology optimization by which you can optimize the design. So it's not that I need a completely filled material here. It can be hollow in some places without compromising on the mechanical strength. So these things can be done only in AM. Second is such a complex design in additive manufacturing, or sorry, in a conventional way, if you have to manufacture, subtractive manufacturing, you can do only one phase like this, correct? And if there is a hole which is needed through this, say the hole will be a U-shaped hole like this. I cannot drill a U-shaped hole in a conventional way at all. Design itself is like this. I cannot drill like this, then go inside like this, come back like this, not possible. Only I can drill a hole, a straight hole. Whereas in additive manufacturing, your internal channels can be of any shape. So by which your overall dimension of your product also can be reduced. Next is, we prepare this particular file, check for the stress points and what will be the stress, whether they can give the mechanical strength. So predominantly academic side you use ANSYS, but we use something called as material magics, which is much more advanced and things like that. We use that. Sometimes we rely on ANSYS also. So we do all this particular simulation, and then the critical part comes is I cannot straight away go print it. So if I have got a filament, I should know what is the melting point of it, what is the time required for cooling, and what can be the layer thickness. So there are, I cannot explain it here, but there are around 1,000 different parameters which needs to be set right for 3D printing. So we need to have control on the process parameters and then print the component. So now in additive manufacturing, final product is not readily printed. So once it is printed, you need to take out the support structures. If the surface is rushed, you need to still do conventional machining, polishing, buffing and all those kind of things. And finally, that will go into quality inspection, where that will be compared with your actual drawings, and then the quality will be assessed. So additive manufacturing is not a simple process, it is again a complex process, but it is much faster compared to conventional manufacturing. Though initial cost might be higher, but for prototyping, proving out everything, it is much faster. I'll just give you a couple of examples also. Um, Now say, you know this Chetak helicopters, no? Which our defense uses. It's a very old helicopter. Now the source country, I'll not name the helicopter, some aerospace, some aircraft has been procured from some other countries. So now that country has already got an upgraded version, they are no more using that at all. Now tomorrow if I need a spare for it, if it has failed, then I cannot produce. I need to depend on the manufacturer who is from another country. And suppose imagine that we are already in a war with them and we need spares, will we get it? No. So there is another concept in additive manufacturing called as reverse engineering, and one more thing called as digital inventory. So reverse engineering is, I have this product but I don't have the design file, I don't know what material it is, I don't know what is the tolerances, nothing. So typically we take up such kind of projects. What we do is first take this model, use a 3D scanner, scan it and generate a model out of it. Then go to the application side, see where this product gets fixed there. There we check for all the tolerances, other things. We design it, we cut the components, study the material composition, find out which material it is, and then reproduce it. So like this, for Indian defense, we have identified around 16 different components, which we are the digital inventory for them. So what used to happen before this is, say they want one component which goes into a helicopter. Now they go to the manufacturer who's somewhere, say example in Russia, and tell him that I need this component. He will say, I cannot give you one component and all. You need to buy minimum 100. And I'll be able to supply you in 6 months or 1 year's time. So now only for one component, I am procuring 100 numbers with a timeline of 1 year. So slowly over the last 10 years, we have worked very closely with all the defense organization, and we started identifying such critical components. We took it, we did the reverse engineering, we did everything, and we proved it also. Because if it has to go into a helicopter and it is going to fly, we need a lot of certifications, and there is a separate certifying body called as Semilac also. Without their certification or approval, you cannot fit any component in the flying or defense organizations. So far we have qualified around 16 such kind of components, which we can supply to the defense off the shelf. Now the advantage you see, they don't have to buy in bulk, they don't have to wait for 1 year. Even if they want one component, they will tell us. So we are a digital inventory. So in our servers with all the safety, the complete design, parameters, everything is stored. So they want one component also, we print one component and give it to them, 1 week time. So like this, there are several use cases in industries, whether it is steel industry, cement industry. They might have bought a very expensive hydraulic pump, but after 10 years, the manufacturer has upgraded. He doesn't have spare. What will they do to repair the old pumps? They cannot simply leave 1 crore, 2 crore worth of material like that. So this technology is gaining popularity very, very widely. So while additive manufacturing, you can see point by point here. One is customization. The way you want, you design it, you print it, you test it. Weight reduction. So I was telling you about the LPSC rocket launch here. It's a rocket part which was hot tested. Earlier conventional manufacturing, it used to weigh around 500 kgs. After additive manufacturing, it is weighing around 15 kgs. Weight reduction. So just imagine If this component has to fly in the space for 1 year or 2 years, the amount of fuel required for it to escape from the gravitational force of the earth itself will become huge. When there is such tremendous weight reduction, your efficiency, cost saving will be totally to the next level. Next, optimized post processing. So it is not that everything you need to 3D print. Some of the conventional thing you can first 3D print and then you can do the post processing like drilling, milling, cutting, everything can be done outside also. Functional performance can be improved. Just one more case example which we have done around 7 to 8 years back was a radio frequency antenna which is on a satellite. So previously it used to be done in conventional way, but due to the number of welding joints, multiple components screwed in together, there used to be a lot of radio frequency leakages. When that was 3D printed as a monolithic structure means there is no welding joints, no multiple. It is built itself as a one component. So efficiency can be improved in such cases. So you can achieve the optimal design without compromising on the mechanical strength, which we call it as topology optimization. Next is response time to, that is design to realization of your product. Unlike conventional, you don't have to wait for making the mold, casting it, or taking a huge block, do CNC operation. No, you have the design file ready. You can straight away 3D print it and have your component within 1 or 2 days also possible. So if there is any changes on your final design, conventional you want to do, you need to change the entire mold, which will become very expensive. But here you can simply change the design, reprint it again. There is no tools required. So for different sizes of hole, different sizes of shape, you don't need separate tools. It is just a printing process. So it's a toolless design. Compared to casted metals, this will give you much better mechanical properties. But again, forging is superior, but additive manufacturing is between forging and casting. So it is better than casting. So as I told, you can have a monolithic structure. So just to show you, I don't know if you can see it from here. See, this is printed in one go. There is no screw in, no attachments, nothing, but it is printed in one simple structure. It's a dragon thing which has been 3D printed. So you don't need to do the fixing, arranging, nothing. You print it and start using it. So any complex design, you don't have to do multiple joints, but it can be a monolithic design. Supply chain issues, which I just told you about the defense organization, it can happen with any organization. Not much of a maintenance required. Generally materials, any material which can be welded can be printed. Simple technique. If that material can be welded, then it can be 3D printed also. Faster design iterations, so you don't have to get into again conventional things. Flexible production, so anytime you can start, stop, you can do anything. Any absolute or legacy parts which is no more in production, those design files you can recreate it and again reproduce the component. Now, that I have given just a basic of additive manufacturing to you all. But some of the universities across the globe, additive manufacturing is one of the uh, what do you say, hottest topic in research, because the end applications are tremendous. You will not imagine, it is so tremendous. So many universities are working towards it. Now in India also, it's not that nobody is working. Indian institutes and universities are also working, but you can literally count them on fingers. For such a big nation with such number of institutions and universities, there are very few institutions who are really doing a lot of research. So this is one Carnegie Mellon University. So they are basically only working on additive manufacturing for robotics and automation. So when it comes to a robot, a different kind of body. So whatever I was saying on the collaborative robots. So different materials and such kind of things. They are doing a lot of research. They are also into bioprinting. So today's generation, you can even print cells, live cells also you can print and mass produce from it. So probably in the very near future, you can print organs also. So and even in electronic applications, again, additive manufacturing, it's not only for mechanical. So many people are working, so they are also working on electronic application where, say, PCB. You want to build your own PCB, you don't have to get into Gerber design and that, this and all. You can straight away print a PCB board with a 3D printer. Just like you have a normal paper printer, tomorrow you'll have a 3D printer for printing PCBs. And over the years, semiconductors, which can print 1 micron, 2 micron layers and all possible. Then there is another institute which is mainly working on breakthrough materials and computational methods. Now, as I told you, when right now the software can design supporting structures, orientation, but at the same time, it has got a lot of scope for optimization again in the future. So many people are only working on developing AI, ML, and data science models, analytical models, which can assist 3D printing. Now, say for example, some of the design in the simulation it will be successful, but when I start practically building it up, there may be some external factors which will fail the build. Say for example, why I tell computational is so important. Now, say imagine I have to build this product. I start from this layer. Imagine this will be built with 30 or 40 micron layer thickness. Um, how much 30 40 is known? Everybody knows. 30 or 40 micron thickness. Sometimes you see dust particles on your mobile screen, no? That one particle size which can be visibly seen is 100 microns. Anything below 100 microns, you are not be able to physically see it also. So when we are building this, we in our factory we build component of this height also. So now imagine I'm building this 300, 300, 300. To print this entire component, it is taking me 3 weeks to 4 weeks time, one component. Now imagine it prints till here, and during printing the top layer it fails. Then whatever 3 weeks I have spent, it's gone. So we need more and more analytical models to predict failures, which some of the universities are really working into. Now they are working mainly on cyber physical systems. So where uh, now discussions are going on that every ship, INS Vikrant and such kind of battleground ships should have a 3D printer, or every space station or every rocket which launches with humans in it. So they're a 3D printer. The reason is you don't have to carry multiple things. Whatever you need, you print it. As simple as that. So they are mainly working on security of such kind of system. So tomorrow in space something is there and I can hack it from here. They want to print a knife, I print a gun for them. It's risky. So cyber physical systems are very, very important. And we are also into something called as tissue mimicking materials. So self-healing materials or how your tissue behaves, the same way a material can mimic. And right now, Wipro is also into a project where we are working on something called as soluble implants. Now, in some cases, they fix nut and bolt when the bone is broken. That they do it with one surgery. But after complete healing, we do another surgery to take out that. So we are with some German institution, we are working on um, type of material which will get soluble with your blood cells when you take a medicine or something. So lot of research are going into such kind of things. So the next is lattice design. So anybody knows what is lattice design? Okay, just to give you an example, earlier days whenever we used to construct house, the bricks used to be completely solid, completely solid. Nowadays you can see hollow bricks also. So hollow bricks less material consumption, lighter in weight, but it will give the same strength. So same way in mechanical component also. Now if I have to print a part something, now I don't have to completely fill it with metal. Internally it can be a separate honeycomb structure or grid design or any organic design which will not deteriorate the mechanical strength. So such kind of internal structures are called as lattice structures which will produce or give you strength for the materials. So a dedicated uh, team will be working only on optimizing such kind of things. Next, in a University of Texas, they are working on hybrid AM. So today we have got a process, say for example, I want to print copper, then I can print a component completely with copper. If I want Inconel, I can print one component only with Inconel. I don't have a process where one part I print with copper and one part with Inconel. So there is again a huge opportunity where multi-material printing. Some research areas are there. Larger area AM means right now the biggest additive manufacturing machine what is available in the market is 1 meter by 1 meter by 1.5 meter. That is the biggest size. Now if I have to produce an entire rocket in one go, with the present technology the limitations are there. So people are working on that so that I can print a 50-foot container probably 3D printed. It is possible, but we have to get a breakthrough over it. That's all. And even ceramic based printing is gaining a lot of popularity because ceramic is not reactive to human inside. So implants can be in the future can be ceramic also. This is just for your reference. Now all these particular universities, they have not achieved overnight success. So they have all started very long time back and they are still pursuing on certain focus areas and developments are happening. So this is one area which has got tremendous scope for research, career, everything. The reason is though the technology was old, people have realized the real use of it, application of it, and personally we have seen being in the business last 3 to 4 years. Till that time, our only customers were defense, aerospace. Nobody else used to wanted to adapt additive manufacturing. But in the recent times, whether it is automotive company, oil and gas company, hydraulic company, medical, even academics, everybody has started using this because it's a easier way to do things nowadays. So additive manufacturing has got its own um, space in the manufacturing place now. So whatever earlier was only 1% market share was additive manufacturing in the manufacturing business. Today that has increased to 15 to 20%. So you go to Ola, you go to Mahindra, you go to Nissan, you go to Maruti, you go to Jindal Steel. Everybody have got 3D printing adapted into their particular process. So in the future, this trend will continue to grow. Will continue to grow into a certain extent where any field will have a 3D printer, and I would say that every home will have one 3D printer in the future, because you want to buy something, you want to do something, for everything you don't have to buy everything, you can print it on your own. So with this, some of the key takeaways for academia, I just listed it. So there are a lot of case studies also where universities, scholars, researchers, faculties, or students who started with a small uh, startup, today it has become very, very big companies also. So whatever you can see here, no, these are all company names, and these all have started as a university startup. See, students or faculties, anybody have started this in a university. Today it has become a multi-billionaire companies into 3D printing. So that's all from my side, but I'll give you a few inputs where you can get a bit more benefited. So since last September, Wipro has started one program for educating everybody on additive manufacturing. So every third Thursdays of a month, afternoon 1.5 hour session will be webinars on various different topics. So last month it was on space. So this month theme will be different, and again next month theme will be different. So every month, third Thursday from 3 to 4, a free webinar will be there. So you can just simply go to LinkedIn, search for Wipro 3D. There you will get all the Thursdays. You can register and you can attend the webinar. We did it in September, which was a good success. Now we are starting again in November. So we call it as every Saturday will be a separate topic. So November 9th, the first Saturday will be on additive manufacturing fundamentals. 16th will be design for additive manufacturing. 23rd November will be material and process parameters. And November 30th will be part identification. So 4 different topics on 4 different Saturdays. So but this particular complete day session, you can opt for offline or else online, but that will be chargeable. But anybody from academics who are interested to take up any course, you can get in touch with me. I can give you coupon codes where you'll get straight away 50% off on that particular courses. Only for academicians. So that's all from my side. So anything you want to ask me, you can ask. Only one question is not allowed is how much is my salary. Apart from that, you can ask me anything. Leave the session open. Any doubts, automation, robotics, general things, or even additive manufacturing, the session is open. So when there are no questions, only two possible ways. Means I have done my presentation so well, there is no doubts at all. Second is nothing was understandable, so no doubts at all. So I'll consider the first one. But generally, genuinely, if you have any feedback also, you can provide. So first what we do is, generally I'll tell you very openly, we get lot of inquiries on a day-to-day basis that I want to print this, I want to print this. Now first of all, we do a study. So whether really 3D printing is required or not required. So if the design doesn't even have any complexity, so then we straight away say that this doesn't carry any complexity and this is not a part for additive manufacturing. So but in spite of that, somebody wants to do a tensile strength on it or a hardness test on it or a heat treatment test on it, we encourage and we print it. But once they give, we first ask is in which material do you want to print this? So if our customers are not very much sure on the material also, then we start discussing on where is that this is going to be used. Based on that, we provide our suggestions. You better go for polymer, metal, which material, everything, and accordingly it can be done. Recent case in MIT, Manipal. So they wanted something to be built for their robot, which they have done a crawling robot. So they wanted the outer housing of this to be printed. So earlier they designed it in such a way that multiple parts, because while crawling it will bend and everything. So they designed multiple parts so that they don't touch, break each other. So but when we started discussing with them, we finally figured out that it has to be flexible. So then we printed in a material called as TPU. So TPU is as flexible as your silicon phone case. That can also be printed. So that will go fit in properly to their robots. So like this we engage our customers, discuss and then finalize and suggest them. So when it is just after 3D printing, the surface finish will not be very good. It will be somewhere around RA6, RA7 kind of finishing. But if they want a very fine finishing, what we do is, when we 3D print itself, whatever you give me the dimension, thickness you say 10 mm, but I will print it for 10.5 mm or 11 mm, then I will do the machining and give it to you, so that your process will be achieved. With only 3D printing, you may not get a good surface finish, but with good amount of post processing, you will get as good as the machined components. No doubts from the students? So that's all from my side. I forgot to put my slide in this, so probably I just put in my contact details here, and you can get in touch with me. Most of the time I may not be able to attend calls because of the sessions and travel, but you can always drop me a WhatsApp message and I'll be able to respond to you. So that's it from my side. Thank you.
I would like to invite Mr. Krishna to give a feedback on the session.
Positive, negative, both will work, sir.
Good afternoon. Thank you for giving me to the opportunity to give the feedback. Mr. Santosh MS provided an excellent overview of automation, robotics, and 3D printing. His in-depth, excellent explanation of additive manufacturing was particularly impressive. The session was well structured and engaging. He effectively explained complex concepts and provided real-world examples. The interactive approach allowed for better understanding. The session was valuable for learning about the latest advancements in these fields, and Mr. Santosh's expertise and passion for the subject were evident throughout the session. Thank you.
Thank you, sir. Then I invite now Ms. for Robotics.
Good afternoon to all. On behalf of GIT, it is my honor and privilege to extend a heartfelt thank you to Mr. Santosh MS for delivering such an insightful and thought-provoking session on automation and robotics. Your expertise and deep understanding of the technology and its real-world applications have enlightened us all. You have successfully demonstrated the vast potential of 3D printing. Your words have not only inspired us, but also have encouraged us to explore this technology in our own field. The practical examples and industrial insights you shared have provided us with valuable takeaways and we can apply to our work. Thank you once again for taking the time to share your knowledge with us today. We truly appreciate your dedication to advancing technology. Thank you, sir.
I would like to welcome our director, Sarisa, to express GIT's love and gratitude for this wonderful